Okay, so on to quantum particles then. So it's often argued that quantum particles are not individuals because if they were, they would violate PII. Right, so the idea is, suppose they're individuals, look, but they can have all the same properties, so they can't be individuals. Therefore, implicitly, we're rejecting transcendental individuation if we make that argument. Right? So, the facts about quantum mechanics that are relevant here are that the permutation postulate says that the permutation operators commute with every observable. That most people think that the probabilistic weighting of states suggests that that states that differ only with respect to the permutation of particles are not really distinct states. But of course, there's a distinction between different kinds of particles. Electrons obey the Pauli exclusion principle, photons don't. So the two types of statistics place different restrictions on the states of combined systems, but the argument is either way, neither type of statistic allows you to count as distinct a state that differs only by the permutation of two particles. So, for bosons, we can say, look, they can be in exactly the same state, right? They can all be piled up in the same state, as many of them as you like. So, we're not going to, it seems obvious that they violate PII. For fermions, well, think about two electrons in the first orbital of an atom. They have the same wave function. They are in the singlet state of spin. So when we look at the reduced density matrix, which is the only thing we can attribute to each of them separately, for the reduced density matrix for its spin state, they'll be the same. They'll both be the maximally mixed state. So they violate PII. They have exactly the same states as each other. So that's the received view. So you get Schrödinger saying particles lack individuality, and you get Weil saying the same thing. However, Weil says something else that's in tension with that. Steve French often quotes this, and he stops at the exclamation mark there. But Simon Saunders and Fred Muller said, right, but look what he says afterwards. Afterwards, he says they satisfy PII because they obey the exclusion principle. How does that... well, he doesn't say that, but then elsewhere he refers to the Leibniz-Pauli exclusion principle. Now, it's confusing, right? There is one way you could think about the exclusion principle, the sort of old way of thinking about it, where you think, what's the exclusion principle say? Where it says no two fermions can have the same set of quantum numbers. That sounds quite a lot like PII, doesn't it? It sounds like you're saying they can't have the same state as each other. So it sounds like they satisfy PII after all. But then Margenau says, no, that's wrong. People have thought that the exclusion principle's got something to do with satisfaction of PII, but it's incorrect. So what I want to talk about in increasing detail is this controversy about PII and quantum mechanics and the debate about it in the recent literature. And the debate was started by Simon Saunders, who challenged this received view. And Simon says, first of all, he says, well, there's this idea that classical statistics involves particle individuality, quantum statistics doesn't, that's wrong. The Gibbs paradox is supposed to be resolved by denying classical particles individuality. But the really important thing for my purposes is what he says in 2006, where he introduces the idea of weakly discernible. And I'm going to explain this in excruciating detail probably. So on this slide I'm just referring to weakly discernible without telling you precisely what it is yet, but I will, don't worry. Okay? So he says, okay, look, there's this other kind of discernibility, weak discernibility, and fermions satisfy it. Therefore the received view is wrong, and they do satisfy PII after all. And the idea is they can be discerned by states like has opposite spin in direction x. Then Saunders and Muller in 2008 went further and articulated this